Okay, what I have planned for today is to introduce project 2. So I'm recording this so you guys can go back and review it, okay? There's a set of slides. I've released the module for the slides, and we'll be releasing the assignments for project 2 here before the end of the day. And it's very similar to what we did with project 1. I'll give you basically some assignments that are modules that will help you in the project. They won't be exactly what you need, but you'll need to modify them for the final project, excuse me. So this is the second project, and students usually really like this project. So I hope that you guys have a fun time with it. And let me share my screen real quick. Okay, so this project is an introduction into image processing. And what we will use, so for you to learn and continue learning Python, is a problem that clinicians run into is this a melanoma or a mole? So the idea is you'll take an image or use images of a mole or melanoma, and you'll quickly determine using an algorithm whether its risk level. Is it, and we'll use kind of a 3 levels of risk, green being it's not very suspect, yellow is it's suspect, and you will need to check this with a clinician, and red is, oh, this looks like a melanoma. So that's the idea. I believe you guys understand what melanoma is. It's skin cancer. It's very prevalent in all different types of areas, from people that have very fair skin to people who have very dark skin. So in fact, I had my best friend from high school just the last 6 months was diagnosed with melanoma and had spread to its lymph node. So this is kind of a personal thing for me. I've been working on this project for many years, and how can we come up with a simple algorithm to really determine the risk level associated with a skin lesion? So you'll be developing the software to do that. Once again, skin cancer is prevalent in people of color. You don't have to just have fair skin. In fact, if you have skin cancer and you have darker skin, the mortality rate, the death rate is higher because you tend to go longer before you have it checked by a doctor. So that's kind of an interesting observation. Okay, what is a mole? A normal mole is usually an evenly colored brown, tan, or black spot on the skin. It can be flat or raised, and many of you probably already have moles, probably most of you. It's generally less than 6 millimeters, which is about 1/4 inch. And some moles can be present at birth. I have some of those, but most appear during childhood or young adulthood. New moles that appear later in life should be checked by a clinician or doctor. Possible signs and symptoms of melanoma. The most important warning sign is the melanoma is a new spot on the skin or a spot that is changing in size. Okay. Another important sign is a spot that looks different from all other spots on your skin, known as the ugly duckling. Okay. So if you visually were to check a mole, there's this acronym that to follow that doctors have in their mind. They're looking for A, B, C, D, and E. A is for asymmetry. One half of a mole or birthmark does not match the other side. B is for how jagged the edges of the border is. C is color. Is the mole or lesion all the same color? Are there gradients varying from red to brown to black? And D is for diameter. Is it greater than 6 millimeters? And if you want to have a visual picture of how big 6 millimeters is, that's about the size of a pencil eraser. And then E is evolving. The mole is changing in shape, color. So here it is, kind of a view of what A, B, C, D, E is. Very symmetric. Borders are uneven down here. This one has multiple colors. The left side is darker, has some some darker gradients in it. The right side is lighter. Diameter, this is large, it has gradients, it has a rough border. And then evolving, here's an example of one changing over time. So we're going to use image processing to come up with a risk score for a set of images of lesions, which are mole or melanoma and in between. So there's going to be maybe 3 assignments here, and then your final project. We will not do all of the A, B, C, D, E. We will do asymmetry. We'll come up with an algorithm for determining how symmetric the lesion is or how asymmetric it is. Come up with an algorithm for how jagged the borders are. And the bonus for the project will be color. So this one we will do, but it'll be a bonus in your project of 5%. So that's kind of cool. And diameter, that's kind of an easy one, but we won't do that one, or E, which is evolving. So we will use a technique called binary large object blob processing, and it involves thresholding and histograms, and you will learn these basics. This blob image processing has been around for 40 years, so it's very well known. There are modules out there for Python that we can use and leverage. A lot of good examples. So we will introduce image processing in this application. So what you will do in assignment 1 is you will basically do a histogram. You'll validate that you have the right module. So you need to maybe install this module, but if you have Anaconda, you should have the scikit image module already installed, okay? If you don't have it, you might have to install it. You'll read an image file, and I'll show you some examples of that. You'll convert what's called the RGB image, the red, green, blue image. Really, it's a large array. It's 3 different colors, 3 different arrays representing the red plane, the green, and blue plane. You'll convert that to a grayscale image, which is 1 array, 2-dimensional array, and then you'll process that grayscale image. And you'll do a function, you'll perform a function called a histogram, and then plot the results. You'll threshold the image and to create what's called a binary image. And a binary image is just that. It's an image of 0 and 1. And grayscale image goes from 0 is 8 bits, and 2 to the 8th is 256 level. So the grayscale image is 256 steps of gray from black to white. Okay. So this is up on the slide set is up under the modules for project 2, and here are some of the modules that you will import for this project. And what you'll do in an assignment 1, here's a hint, is here's what the grayscale image looks like. And I don't know, can anybody give me kind of a quick assessment of where is the pixel value for the mole itself? This dark value here. Where does it show up on the x-axis in the plot? Anybody?
It looks like it's from 0.2 to 4.
Yeah, it's right there. It's that little hump. The background pixels, which are white, right? So this x-axis is the grayscale level. So it's going from 0 to 1. You can think of that as having 256 levels of grayscale, but from a value of 0 to 1, 1 being white, okay? And so the white pixels of the background are this big spike right here. The black or grayscale pixels, and they're really spread. Like was that? I didn't see who answered that, but it was a really good answer, and that it ranges from maybe 0.25 up to 0.45. It's just a small little hump, and that is it's the pixels here. So if you integrate under the curve, it's the number of pixels within that range of grayscale values. And so the largest grayscale value is the background, okay? So if we set a threshold here, and we said everything below 0.5, we want to set to a value of 1, and everything above 0.5 we want to set to 0, what would the image look like? Any guesses? And display that.
I think if I remember correctly from signals and systems, would the colors would switch, like it would get lighter in the middle, and then that would be all that was there. I
Yeah,
think.
that's a good answer. I mean, it's a threshold, right? And everything below the threshold, we're going to set to 1 value. So this dark value, all the dark values would be a 1, which would be white, and all of the background values would be 0, which would be a black. So it would be a binary image, and that's what a binary image is. It has only have 2 values, 1 or 0. What's the advantage of operating on a binary image? In the past, when you didn't have as many as much compute power and memory, you could develop algorithms for the binary image that could be very fast. So that's the history of why there's a lot of binary large object processing routines. Is because computer memory and processing was limited. It allowed you to do faster processing. So if we did just what I said there, okay, so remember our dark object, the part of the null here. So this is the RGB, right? The tone of the skin is kind of pinkish tan. Then we converted it into grayscale. This is what it looked like. And then we did a threshold and made a binary image, and that's what the binary image looks like. And so this is going to be an example output for project 1. Excuse me, assignment 1, project 2. I'm going to give you some real simple images like a heart shape, and have you, if you think about this, okay, the black, in the original image, the black, or in the grayscale image, let's do that. We're doing a histogram of the grayscale. The white background is at 1 already. So you already have a binary image, right? So the white background, there's more pixels that are white. And a pixel, you can think of a pixel as basically, it's an element in a 2D array, right? A pixel value is either 0 and 1 in this case. And so the pixel value up here in this left-hand corner of the grayscale image is white. So there are more white pixels. So we expect this in the histogram, this value to be higher than this guy. And that's all the black pixels, which is the heart itself. If we apply a threshold and binarize it and make the heart, when the value, assign the values of the heart to 1 and the background to 0, create this binary image, it'll look like that. Okay. Why we're doing this is now there's a set of functions that we can apply and say, what would be the area of the heart in pixels? You just count the white pixels, and that's the area. What's the perimeter? There's a function for the perimeter. It would give you the perimeter in pixels, the length of the pixels. So there's all of these functions that then we could apply. What's the centroid? What's the longest line segment? And that's what the blob processing functions do, okay? I'm going to stop there and allow you guys to kind of get into assignment 1 and project 2, and then, or excuse me, project 2, assignment 1, and then on Monday, we will cover the second assignment. And just to give you a heads up of what we're doing here is we'll take our mole image, and then there's these functions. So there's these small little black holes in the blob, and there's functions to fill that. So if we want the area of the whole object, we can then count every pixel. Now, why might you have these little holes in the object itself? Anybody have an answer for that? Here's what the original one. Grayscale looks like. Any guesses? There's little speckles in here, right?
Wouldn't it just be like the color of the original skin, maybe?
It could be the color. Also, it could be light reflecting off of the object, right? Or being absorbed by the object. So it's a way that it could be just you have a speckle or reflection that creates a hole. So there's all these functions, and you can go to sky image measure, and there's all of these functions that you can apply. There's probably 50 of them to be able to measure different things within the blob. And so to get a more accurate image, what we did on this one, or more accurate blob processing, is that we fill the holes. The other thing is we can remove small binary objects out in the background. So if you have like a reflection off the skin that's a really small white spot, and we remove all of the small binary large objects, and are left with the largest one. So there's all these functions to be able to do that. So I'll be releasing the template code, or the project 2 assignment 1, and it's very simple. You load up an image properly using the proper functions to load an image, load up the modules first, and then load up an image, display it, perform a histogram, and you're done. So that's the first assignment, pretty straightforward. Okay, I'm going to stop here today. And if there's any questions about the assignments coming up, or if there's any questions about project 1, which you guys just turned in, I gave you guys an extra day. I hope that that was appreciated. You can stick around for those questions. How did things go with critique? Pretty straightforward?
Yeah, it's pretty easy to use.
Yeah, have anybody started their peer reviews yet? I think they may actually go live as soon as you turn them in. I don't remember how they do that. You have a few peer reviews you'll need to do. Let's see. Oh, showing you guys my schedule. You don't really want to look at the schedule. That's why I require you to send me an invite. Okay. Hold on, let me pull up a critique here. Let me take a look at how you guys are doing with your submissions. Okay, it looks like people have been given their evaluations, 3 evaluations. Okay. Looks like everybody turned something in. Awesome. All right, any questions, guys?
Do you know when assignment 1 will be due?
Probably Monday night, so you'll have all day Monday. It's a really simple. It's just making sure you got the right modules and you can do a threshold.
Okay, thank you.
Yeah, I'll have it posted by the end of the day, and it'll be by the end of Monday. That's what my plan was. The other ones I don't have set yet because I have to adopt it from the 6-week to a 10-week. And I'm always worried that we're going to run out of time. So I have to do a little calculation on when I think the next ones will be done. Okay. But this project, I think, is simpler than the wearable project. Okay. All right, you guys have a really good weekend. I hope you get a chance to have some fun this weekend.
Thank you.
Take care, guys.